So producing the optimal solution is unfortunately not really the end of the process. We still need to see whether the optimal solution is really optimal or not. Well, supposedly this process will create an optimal solution, but what happens if we change the constraint by a little bit? What happens if we change the coefficient of a particular decision variable by a little bit? Will the solution change by a lot? So we just want to see if the optimal solution is stable among all the possible variation of all those elements. So we can perform that by using a technique called sensitivity analysis. So we ask a lot of what if questions. So what if we change this value? What if we change this coefficient? What's going to happen to the optimal solution? So that's the essence of the sensitivity analysis. When you use solver, you can specify this for the solver to produce a sensitivity report. And the sensitivity report focuses on two things: the coefficients of the objective and also the right-hand side of the constraints. So what does that mean? Well, it's hard to understand what I'm talking about just by looking at the charts and listen to my watching my lectures. But when you do the examples in the book and when you do the practices, then you know exactly what that means. So I just want to highlight some of the things so that you can pay attention to those important areas when you're looking at the sensitivity report, when you're going through the examples. So every objective function is expressed as a linear function of all the decision variables. So each decision variable actually has a coefficient. So the coefficient of that variable basically determines how strong or what is the impact of that decision variable on the objective. So the first part of the sensitivity report shows that. And there's one thing that's important, that's the reduced cost. If the decision variable is either 0 or at its upper bound, that is the upper limit of whatever value that it can take on when you produce the optimal solution. So let's say that the decision variable values happens to be 0 when the solution is optimal. Then this item, reduced cost, indicates how much better the coefficient must be before the optimal solution will increase. But if the decision variable happens to be at the upper bound, then the reduced cost item value tells how much worse will this coefficient has to be before the optimal solution will decrease. So that's what the reduced cost means. Again, it may not mean much to you at this moment, but when you actually go through that example, then you should see exactly what the reduced cost will do for you. And then the second one is the second one of the analysis report is on the constraints. So that's at the bottom part of the report. So the thing to focus on is something called a shadow price. So shadow price indicates the change in the optimal value of the objectives when the right-hand side of the constraint changes by 1 unit. This again only applies to those constraints at the boundary. So if the constraint actually is bounded, meaning that if you say that you can only spend $10 of fuel going from place A to place B, and the optimal solution actually requires you to spend that $10, then it means that the constraint is at a bound state. It's a bounded constraint. Then the shadow price tells you what if you let's say relax that condition $10 by 1 unit. Let's say if you increase that from $10 to $11, so what would be how much improvement will you see in the optimal solution? So that's what the shadow price means. Again, you may not quite understand what these terms are and how that fit into the whole picture, but just keep those things in mind when you go through the examples. A second way to in this book, another way to do sensitive analysis is through the add-in called the solver table. The solver table offers a data table like sensitive analysis. So you can actually specify a range of possible values and what increment, and you can see when you put in all those different values to the coefficient or to the constraints, what would be the new optimal solution, and you can compare and contrast the changes to the changes to the optimal solution. So we talked about how to produce the optimal solution. What is the process of optimization? Uh, when you get the result, even after sensitive analysis that shows that the result, the optimization result, is stable, then there's a few things that you can still use to interpret the result. These are actually quite important, especially if you're looking at a real business problems. First of all, if when the constraint is binding, meaning that the constraint reaching its limit, just like my last example of driving, when you say that one of the constraints is the amount of fuel, or the total amount of the fuel that you want to pay for. So when you find the optimal solution for your travel time, let's say that it reaches, so that constraint reaches its limit, so you have to spend $10 on fuel in order to reach the optimal travel time. Then we say that the constraint is binding. So when the constraint is binding, it means it's more than likely that it is the resource that limits the objective from improving. So when you see that you have to spend $10 in fuel in order to reach the optimal route. So maybe if you spend a dollar more, the route can be improved, but you can't do that simply because that is the limit that you give to this problem. So when the constraint is binding, it usually indicates that particular resource that's actually limiting the objective from improving. Also, when you add a new constraint, or when you make an existing constraint more restrictive, you always get a worse objective. So it means that the optimal is always worse. It's always worsened when you add a new constraint, or when you make the constraints more restrictive. This is intuitive, but sometimes people don't quite understand that, or I think it's probably more important to just keep this in mind as a common sense debugging tool. So if you add a new constraint and the optimal solution actually improves, then you know something is wrong. We only talk about linear models. The linear models means that those models are scalable and additive. So there's a section in the book that talks about linear models. Linear models are the simplest kind of optimization models. So we're not going into any deeper analysis using very complex models. But in a lot of cases actually in business, linear models can produce good solutions and insights for us. So we're going to only focus on linear models. And finally, even if you build a very reasonable model, it doesn't mean that you can always have a solution. So sometimes there's no solution at all. That rarely happens, but it does happen. So when things like this happen, don't be so surprised. You always want to go back and check whether the algebra or whether the formulas are correct. But it's possible that a reasonable model would not have a solution. So optimization finds applications all around you. So if you look carefully, you'll see that there are many different issues that in business that can be optimized or can be formulated into an optimization problem. And you also notice that most organizations don't really apply optimization to those problems. They usually just come up with a half-baked solution and making sure that things don't break down, or at least it will they'll do things in an acceptable way. Hopefully after this course you will be able to identify those problems and formulate them into an optimization problem and start solving them. So we can't cover them all because there are too many different types, but in this course we'll talk about a few of them. For example, the product mix model, which is probably the most general one, general style optimization problem. We use that as the example in this session to go through how solver works. And then in the next session, we'll cover a few others, which actually in chapter 14 of the book. So there's scheduling models, blending models, and financial models. So those will be the extended models covered in the following session. There are, of course, a lot more, such as multi-period models and logistic model, but I specifically um, name one set of models as optional in the next session. That's the integer optimization model, which is very useful, but it's considerably harder than linear programming. So spend your time, please make sure that you understand not only the how solver works, but also how to model different business problems by formulating an optimization problem, by identifying the objective function, the decision variable and constraints. And this will be a really useful technique going forward because you will be able to solve a lot of problems that you encounter in business.